Right? Like most of Algebra 2 is kind of organized into each chapter is a different kind of a function. And so this is the chapter about what they call rational functions. And actually, each chapter is kind of divided into, there's part of it that'll talk about functions. There's part of it that'll talk about equations, and there's part of it that will talk about expressions. Right? The part that we're going to do now is functions. And by functions, what we mean is this is something that y equals, and then there'll be a rational expression on the other side. Right? And what do you do with functions? You graph them. I mean, that's what you do with a function. You graph it. You solve equations, you graph functions, you simplify expressions. My guess is that what we're doing in this right here, you may not think that this is actually all that hard today. The hard part of this chapter is the simplifying expressions, right? Because, I think I got this in here. Rational functions, you should remember, when we say rational, it means can be written as a fraction. So you got to think, when it says rational, you think fractions. And when you start simplifying rational expressions, that means you're going to have to add, subtract, multiply, and divide fractions. But now it's not going to be fractions of numbers. It's going to be fractions that have variable expressions in them, right? And that, if you struggle at all with just plain old fractions, and most students do, then it gets harder when you have to do it with variables. Okay. I think this part, which is just the graphing of it, I think you'll probably think it's not that hard. I hope so. All right, so rational functions are functions that can be written like a fraction. And the fraction in the numerator would have a polynomial, and the denominator would have a polynomial, right? And always, it would say after that, it would say, in this case, it's p of x divided by q of x. It says q of x does not equal 0. Why would they say that? Right, you can't divide by 0, right? So when that's the thing that you have to be on the alert for, is always you can't divide by 0. So they're always going to say, if you got a q of x in the denominator, make sure the denominator doesn't equal 0. Now the thing about rational functions is their graphs can be all over the board. I mean, up till now, we've done a bunch of graphs that had very predictable shapes, and we just moved them around by adding a number here, multiplying by a number there, putting a minus sign in front. It's hard to do that with rational functions because all of their graphs are different, except one. Okay, so we do two sections today. The first section is the one very predictable graph of a rational function. And then the rest we discuss in the second section, which we don't actually graph them. We just talk about the important parts. Okay. Again, if you haven't been in my class before, there will be this video, and then once I've written on all of these slides here, then these will be posted on the website too. So if you want to have notes, if you can print them out, you can do it that way too. You got to think of the balance between how much am I getting out of writing this note versus how much am I getting out of actually paying attention and trying to understand. I mean, everybody who sits in a class, myself included in college, I mean, you had to decide how much am I getting out of this and how much am I getting out of just concentrating on what's being said, especially if you could actually go back and watch it again. We okay? There's nothing you really need to know in this. The note part will start here. Okay, the rational function that is actually got a standard shape that we want to know is called an inverse variation. And I'll say in this book, they actually give it another term. They call it a reciprocal function. Well, if you look at it, it says y equals k divided by x. Okay, and x does not equal 0 because we don't want to divide by 0. The k is a constant, right? That's a common way to say there's a number there. It's not a variable, right? Variables vary. They change, right? We only have two variables there, x and y. K is a constant. mean it doesn't change. Examples would be y equals 2 over x, y equals 4 over x, right? There's going to be a number there, right? You're not going to deal with a k. It'll be a number. Now, if you look at a fraction like this, right, y equals 2 divided by x, what would happen to the value of y if I made the denominator bigger? What happens to the fraction if the denominator gets bigger? Does it get bigger or does it get smaller? Right? If I say 1/2 versus 1/8, which is bigger? The half, right? The smaller the denominator, the bigger the value of the fraction. So as x gets bigger, y gets smaller. As x gets smaller, y gets bigger. That's why it says inverse variation. They are varying in opposite ways. Okay, that's inverse, right? So inverse variation, I've graphed 2 of them on this here. Y equals 2 over x and y equals 4 over x. The 4 over x is the more solid line right there. But notice the difference in the shape. By changing the 2 to a 4, did it change the basic shape very much? No, it doesn't. It doesn't much matter what the number is for our purposes here. Okay, it's still going to look like there's 2 what you call branches, right? That's a branch. That's a branch. Right? There's 2 branches. One of them is in the first quadrant. One of them is in the third quadrant. Right? And that'll be the same no matter what that number is in the front. You know, if you try to think of it in terms of the graphs and the transformations that we did with other functions, you might want to say, oh, that's a stretch. We're multiplying by a number. But it's not. That's not the multiplying by a number part. That's just part of the parent function. The 2 or 4, you know, there's got to be something there. So don't think of that like it's a stretch. We won't be stretching or compressing these graphs at all. Are we good? Okay, so the basic parent function, I think all the examples we're using here, we're just going to use 2 over x. We got to use something, so I'm just going to use 2 over x. Right, and what you can notice is we've already said x cannot equal 0, right? Because if it equals 0, you're dividing by 0. So there has to be an asymptote, and we've already dealt with asymptotes, right? We did this with exponentials and logarithms. Right? There is an asymptote on the y-axis because that's where x equals 0. Right? The graph can never touch that line because it cannot, x cannot equal 0. Okay, so vertical asymptote, x equals 0. And in the same way, it has to have a horizontal asymptote because it can never touch the x-axis. Right? If it touches the x-axis, that means y equals 0. But y can't equal 0. Right? Because if a fraction equals 0, it's because the numerator equals 0. But the numerator is, by definition, not 0. It's a constant. It's 2. Right? So no way to touch the y-axis, no way to touch the x-axis. So inverse variations have a vertical asymptote at x equals 0. They've got a horizontal asymptote, y equals 0. Right? The graph, quadrant 1, quadrant 3. So that's the starting point. Now from here, we're going to do what we did with all the other graphs that we did. Right, we're going to see how do we move this thing around by adding numbers, putting minus signs in front, things like that. Got it? So what does it usually do to the graph of a function when you put a minus sign in front? It's a flip, right? So when I put the minus sign here, right, that is a flip. And generally, it's a flip across the x-axis, but this one, it kind of doesn't matter, right? Flip across x-axis. So instead of the graph being in quadrant 1 and 3, now it's in quadrants 2 and 4. So if there's a minus sign, draw each branch in the opposite quadrants, right? Here and here. So that's what it did to the other functions, is what it does here. Put a minus in front, flip across the x-axis. What's that? Put a minus in front of the function, it's flipped. Okay. Okay, what does it normally do to the graph of a function if we subtracted inside? Was it up, down, left, or right? Right, okay. So when it says 2 over x minus 3, that minus 3 is inside the function. So that should move our graph 3 to the right. Now, does that change, does it look like it changed the horizontal asymptote by moving it 3 to the right? That's not right. Got to try this again. I'm probably not going to be able to do this. And the answer is no. The horizontal asymptote is still right here. Right. Does that move the vertical asymptote? If I move the whole graph 3 to the right, doesn't that move the vertical asymptote too? I mean, look at over here. Does it look like the asymptote is still here? No. It looks like it's got to be somewhere over here, and it is. Right? It's got to be somewhere like that. So shifting the graph to the left or the right is going to move that vertical asymptote one way or the other. Now, if you look with respect to those 2 dashed lines that I just drew, it's still quadrant 1, quadrant 3, right? So you just sketch the asymptotes and then sketch in a freehand. There's one branch, there's the other. Done. Right 3. Right 3. Right, and how would we do a left 3? If that was a plus, it would have gone to the left. Okay. How about adding after the function? It's a up, right? So again, we take this graph and we move it up 4. Which asymptote is that going to move? Is it going to move the vertical or the horizontal? It's going to take that line, it's going to move it up 4. Right, so the new horizontal asymptote now is at y equals 4. But the vertical asymptote is still right there. And now if you look at that intersection of the dashed lines, you know, this is drawn in the first quadrant, this is drawn in the third quadrant. Right, just with respect to those dashed lines. Yeah, because we only made one shift. It was a vertical shift. It only moves this asymptote up. Okay, so what is the graph? Tell me what the shifts are you see in this one. First, what's the value of k here? 1, right? Okay, what does the plus 1 do into the graph? Left and down, right? Left 1 and down 2. Right? So when you sketch these graphs, the first thing to do is sketch the asymptotes, right? So we got to, if we're going left 1, that means we want to sketch our asymptote left 1, right? And if we're going down 2, that means you're going to draw this asymptote here. Do you see how that's what happened to the asymptotes because we shifted the graph? Left 1, down 2.
So we're not moving a line, we're moving the asymptote.
Just the asymptotes, right? Now, the graph of the function, because it's positive, is going to be here and here. Done. Right? Just use the red intersection of the red lines like it's the origin and draw in quadrant 1 and quadrant 3. And you don't need to plot points, just get the shape generally correct. Okay. So try to do that one. Sketch a graph, y equals 1 over x minus 4 plus 6. Figure out what the shifts are, draw the asymptotes, and then sketch in the branches. No. I'm not going to pick them up, so you go.
Well, you not picking up, you try them?
Nah, it's a pain in the butt. Sketch graph.
Yeah, you gotta do that.
What's that?
That's a great. Yeah, that helps us.
You want to do that?
Yeah, that can take you from like a good D to a C. You know what I'm saying?
So for those of you that weren't in my class last year, I mean, in order to encourage you to keep up with what I'm doing here, I would collect the U tries at the end. And if you do that, if you want, and then I just give it like a homework grade. You know, that goes in the same bin as your homework. So let's say you don't do your homework. Nobody in here is not going to do their homework, right? But if you like just keeping along, you're going to have 50% right there. And if you want to do it, we can do it. If you want to put more work on me, Dante,
I mean, if you don't mind rating it, yeah, but do it.
I'll do it. Go ahead. If you turn those in, then you know all I want is for you to pay attention and try. I mean, that's it. That was the whole point of doing that. If you think it helps you, yeah, definitely it's going to help your grade. Assuming you'll do more of these than you will your homework, this is going to help. So if you're going to do that, then we need to do it as a class. We'll do it. You need to be doing these on a separate page that you can hand in at the end. And I'm just going to be looking to see that you actually are participating. If you're not, if I don't get something from you, that's going to be a 0. You were sitting there. I mean, you could have done it. I would say go get paper, but well, because these desks are like a barrier right there. So sketch your graph. What are the shifts that you see? What are the shifts? Right 4, up 6. So draw your asymptotes. Right 4, up 6. We're horizontal asymptote. Where am I going to draw this one? This one. Up 6, right? So 4, 5, 6. The vertical asymptote. Right 4. Okay, so that makes just to be clear there, that vertical asymptote is x equals 4. The horizontal asymptote of y equals 6. Okay, then what? Sketch the graph. Where do I sketch it? 1 and be on the lookout if there was a minus in front of that. Their examples just don't have that, but just sketch. The important part of it is you want to make it look coaching that red dashed line, like it's getting close, without touching it, because that's what an asymptote, right?
Now you said it's an
If it had a minus, I mean, what does it usually minus in front? It makes it flip across the x-axis, on it in 2 and 4 instead. The thing you got to look for. Like I say, we're not going to compress. Okay. Well, what if you're given the whole? Okay, now what equation would have made that graph? I mean, if you start 2 over x is the parent function, then you see here, it looks like every grid square is 2. So what is the shift? How much is that to the left? It looks like it's left 3. And then how much is? It looks like it's up 4. Okay, well, how do I show a left? X plus 3 in the denominator and a plus 4 after. Looking at the graph, you should be able to tell that. Easy stuff. Okay, then try to do the same thing. Start over x, and then just put in the right number of it according to this graph. What? There's another U piece of paper to be turned in. How much is it? Right? Looks like it's 1 to the right. What about this? 4 down. Where do you take away 1? In the denominator. 1. Subtract 4, right? Minus 4. This is right 1. 4. Easy stuff. I mean, what you're supposed to notice out of it, we're shifting this around. It's the same way we shifted it. Around. It's like conjugating a verb, right? Once you do the same thing with it. Those who don't know, I speak Italian because my wife is from Italy. And break again. But I think a lot about the way they're pattern like this, how it applies to language. You bet. You ever see my poster over there? What is it? Labyrinth. That comes from there's a quote at the bottom which you wouldn't. That quote says, who's Galileo?
He's designed. The world is
round stars. Ooh, we're all over the board. So this is what it says. This is what it says. Quote that's attributed to Galileo. He says philosophy book, the universe, which stands continually open to our cannot be understood unless one first learns to and read the characters in which it is written in the language of mathematics. Its characters are triangles, circles, and other geometric figures. Humanly impossible to understand a single word of it. One is wandering in a dark labyrinth. Get it? No. Okay. So now we jump to the next section. Of one particular kind of graph of a rational. It's got all the rest of them. And they don't have. I mean, these are 3 different rational functions, so So we can't just like memorize it, and apply our same transformations. We won't be patients. We won't be patients. We won't be. Okay. The thing about them is derived by asymptotes. So that's the one thing that we're supposed to take out. As the rational functions, right? They are by vertical asymptotes, horizontal asymptotes, both. Which we already saw that, right? We had one that had.
Is that whole thing going to be on the video? No, the teaching is me.
Yeah. Everything being recorded.
Okay.
Spontaneous.
Oh, darn.
It's going to be recorded.
I went to church yesterday.
Really? At Tuesday? On a Wednesday?
Bible study.
Anything?
Yeah.
Really?
I did.
Are we gonna?
I did.
Are we gonna?
I don't know about all that. I gotta know more stuff.
Oh, you're funny. So the first, they talk in terms of points of discontinuity. They don't really say that in the SOLs. In the SOLs, they really talk horizontal asymptotes, concepts that we are already familiar. The truth is that there's two kinds of points, which are x values, where the graph, like we've already seen on an inverse variation, two branches. Okay. Can't draw that graph with one continuous pen and draw the other part. So it's a discontinuous, and the x value where it's discontinuous, right? That's where you pick up the pen and you move. Other kind of discontinuity it's not a vertical asymptote because know what the graph does. It approaches that line. It's either going negative infinity or off towards positive infinity, whole, right? And you still can't draw that pen, right? You could draw it up to here, and then you'd have to draw the rest of it. But the graph is not infinity or negative infinity. It's just like a continuous. Those are both considered to be continuity. And you would have a hard time understanding if you didn't understand that general term. For the most part, we're more interested in vertical asymptotes than we are asymptotes. Now, you can see what's the difference between you find the points of discontinuity in the denominator. If you remember from chapter 5, the zeros are the points that make. For example, this one, since there's an x planar, what is the x value that makes that equal 0? What do you plug? Make x plus 2 equal 0? 0. That's why there's this point of discontinuity at x equals 2. Right? Now, actually an x plus 2 in the numerator also. So simplify this thing, I would have canceled the common factor. So my point of discontinuity looks eliminated. But you still have to put the whole there, function, and you can't divide by 0. Over 0 the denominator. It's a positive. There's nothing to cancel the x minus 2 in the numerator. Hole in the graph, it's a vertical asymptote. X equals.
The number that's like not a part of
You mean afterwards?
Yeah.
That wouldn't be our general polynomial in the numerator, a polynomial in the denominator. We won't have anything being added or subtracted now. Everything will just be numerator over denominator. X plus 4. Remember, the x plus 4 doesn't have anything to do with. Don't even look at the numerator. It's all about the zeros of the denominator. And most of the time, not both. You're going to have to actually solve that. I mean, if I was of this denominator r, then denominator and solve. When we get to these kinds of problems, this, I mean, that is what we have to do, and 90% of the time, the factoring is not the hardest, but sometimes it is. I mean, this is one, in my class, I call this like a simple quadratic, one in front of the x squared. So all you need to think numbers whose product is 3 and their sum is -4. Whose product is +3 and there's two numbers whose product and the sum is -4. 1, -3, right? From that, what are the values of x that make that what value makes 1? So you say x equals 1, and x equals. So when it comes to the vertical asymptote, yeah, for the vertical asymptote, we're going to say x equals 1, x. Right, those are lines. When it comes to answering the question, which they do ask, what is the domain of this thing? You would say it's not equal 1 or 3. There's a vertical asymptote at that point. The graph never has. Didn't do just because that like x minus 1 and x minus 3 is 3. There is the x plus 3 in the numerator. Okay. You got neither one of these cancel 3. So it's not gonna like become a whole asymptote. So remember, whole asymptotes by the zeros of the denominator. Equal to 0, solve. These numbers. Okay. What if I set this equal to x squared plus 1 equals 0, and then I solve x squared equals subtract 1 from both sides. What is x squared? -1. Okay. How do you that? You take the square root of x squared equals the square root of negative. The number is that's got a square root of -1 in it. Imaginary. Okay. We're talking about graph. Are all real numbers. What that tells you is that's imaginary. So no vertical or a whole of the denominator. At least not a real number. We're real numbers. The 0 of the denominator. You can see it. Come on. What's the 0 of the denominator? Right. So this time you set that equal to 0. X equal to 0. So you would say there could be a vertical hole at x equals 4. What is the domain? It's not equal 4. Right. You at that one value, right? Because that would lead to a divide by 0. So, I mean, so if you found a vertical asymptote, you put a not equal in front of it. let's see, we're only going to do one of these. Equal to 0, solve. Tell me what it, tell me what it, tell me what it. Oh, we've done them like this. Come on, Duntavis. Come on, Duntavis. What's that called in the denominator? That called in the denominator. What's x squared minus 6 squared minus 6. You don't even need to use that. You just need to use that. You just need to use that. You just. That's what you're solving. You could solve by factoring, isolating the x squared and taking the square root. Nathan? He's only half right. He says x equals 4. X equals 4. X equals 8? No. That's complete. That's apples and oranges. That's apples and oranges. Wrong kind of apples wrong. Right. It's not apples and oranges wrong. It's half right. What's the other answer? -4. Either you do this, x squared equals 16, and when you get x equals plus or minus 4. Both the plus and the minus. If you factored it, it would have been x plus 4 minus 4 equals 0. -4 and +4 So what's the domain? What's the domain? If the x equals 4 and x equals -4, then the domain domain is x -4 or 4. Else, but it just can't equal those two. Okay. Then we got to deal with a horizontal asymptote. A horizontal not the same thing as a vertical asymptote, just the horizontal asymptote is the value when x becomes really large. It's kind of a different concept. What it means graph. Let's say you have a graph that has a horizontal asymptote on the x-axis. You could have a piece of that graph, the horizontal asymptote, when x is small. But at the ends of the graph, approaching whatever you find for the horizontal asymptote. Vertical asymptote is aligned at absolutely the graph that line. Horizontal asymptote is not that. We had a name for this. The function approaches when x increases towards the left, positive infinity, negative infinity, called the end behavior. Which I know in our different class you may have done a little different, but in our class saw that with polynomials that we would say either it's going up, down, or up and down, or down and up, something like that. But actually, you could think of a horizontal asymptote as the end behavior. What the graph looks like is approaching as it goes towards. So the way to find horizontal asymptote, very easy. It all depends. We've got a polynomial in the numerator and a polynomial in the denominator. It's going to compare the degrees of the numerator. Remember what we mean by the degree. So that's everything is just focused on the numerator. What's the highest power in the denominator? So here we go. Here's our numerator. We have a x to the m plus It could have a bunch of terms that come after, but the highest power, in the denominator, we've got b, which is the highest power term, all the what these are, if the new is less than the denominator, then y is the horizontal asymptote. Basically the numerator has a higher power, or it has a when we did this, right? Y equals 2 over x, right? Which has a higher power? The first, the numerator, which means it's x to the 0. So since the highest power of x, then y equals 0. Horizontal asymptote. Remember the inverse variation. Look. Right. Has a higher power. There is no horizontal asymptote. If it's the highest power in the numerator, it just means this towards infinity, or it's going towards negative infinity. But it doesn't straight line that it's approaching. Complicated of them is, well, what if they have the same power, the same degree? Then it'll be y, the ratio of the coefficients, numbers right there, be y equals that. So here's the examples of it. Okay. Starting with this, y equals x squared over 2x minus 5. What numerator or denominator? The numerator, okay? So by the rules, which rule is it has a higher power? It's this one. It's bigger than the n. So what is the horizontal? There is none. Right? That's all you have. You apply the rule. Since the numerator is bigger, we're going to say no horizontal asymptote. That's crazy. I think I've messed all that up. Y equals 2x over which has the highest power? Numerator. The highest exponent of x. What's the numerator? 1. What's the highest power? 1. So it's the same. So by right, when they're equal, it equals the ratio of the coefficients. Problem. The coefficients in front of x. 2, 1. Right? You don't see if there's a 1 there. See if it be. Y equals 2 over 1, y equals 2. It's 2. If they have the same power, that's it. Okay. What's that? Horizontal asymptotes. Okay. B, which has the highest power, numerator or denominator? Denominator is x squared. Numerator is only x. The rules. When the denominator has a higher power, right? When the numerator is less than y equals 0. Right? So it's got to be one of those, right? It's either if they're the numbers. If the denominator is bigger, it's y equals bigger. It's y equals bigger. None. That's it. So here's the last. Go through quickly here. Has no horizontal asymptote. Which one has no horizontal asymptote? What are you looking for? By the that has no horizontal asymptote. Numerator asymptote. Numerator asymptote. Numerator bigger or the same? Current? Current? Because this is bigger than none. That's it. That's it. None. Which of the remaining two, y equals 0? Has a higher degree than the numerator. That means equals 0. And which is the degree? What is the degree? What is the denominator? 1 and 1 and 1. So what does the rule tell you? Okay, so what is this token? Say again. Over 1, which is negative 2. Negative 2. The horizontal the highest powers of the numerator and denominator. Be careful to question about a horizontal asymptote. Or you need to put the variable that's correct. If you negative 2 and you don't put y equals negative 2 points, because you may think it's going to be vertical, not horizontal. So use the variable for that asymptote. Clear as mud? You like that one? You could use that. Yeah. But the SOLs told us to do. We had to understand how to transform the graphs. We need to know continuous domains and horizontal and vertical asymptotes. Keep streaming. Keep. Check the homework at the beginning of class. So you should have it all. I'll give you a chance to ask questions. Right? If you see you tries, then put your name on it.